Welcome to This Explainer. Today we're taking a wild, mind-bending journey from the hard, observable facts of our universe all the way out to the absolute limits of human understanding. We are going to explore the origin of reality itself, peel back the layers of space and time, and see exactly how far our science can take us, and where ultimately we just hit a brick wall. You know, humanity has been obsessed with the ultimate origin of everything basically forever. Just look at this quote from the ancient philosopher Parmenides, written roughly 2,500 years ago. He argued that absolute nothingness is literally unthinkable, and because of that, the universe simply must be eternal. For millennia, this was just a philosophical or theological debate. But today, well, modern physics and mathematics are giving us some startling new ways to test our deepest intuitions against the actual physical fabric of the cosmos.
So here is our roadmap for this explainer. We're going to cover 1, the firmly known cosmos, 2, the boundary of time, 3, before the Big Bang, 4, infinity and the multiverse, and finally 5, our limits of understanding.
All right, let's jump straight into section 1, the firmly known cosmos, and what modern physics can actually prove.
Thanks to a century of absolute breakthroughs in astronomy, we can trace our universe's history back to a staggering fraction of a second after the Big Bang. We are talking just 10 to the minus 12 seconds in, the electroweak epoch. We know exactly when the very first light elements fused, and precisely when the universe finally cooled down enough for the first light to break free, which was about 380,000 years in. And the ultimate, staggering proof of this empirical history is the cosmic microwave background. This is literally the afterglow of the Big Bang, sitting right at a freezing 2.7255 Kelvin. Actually, fun fact, if you've ever seen the fuzzy static on an old, untuned television set, a small percentage of that static is actually this exact cosmic radiation hitting the antenna. It's crazy to think about, but it provides us with an immaculate snapshot of our cosmic origins, verifying our standard cosmological model to sub-percent precision. This isn't just speculation. This is the universe we firmly know we live in. Which brings us to section 2, the boundary of time, hitting the wall at the Big Bang. Because as we rewind backward past that first fraction of a second, our classical laws of physics completely break down. We hit this absolute boundary, entering the microscopic Planck regime. And suddenly, we have to totally rethink what the word nothing actually means. While philosophers like Sartre debated nothingness as an absence of being, physics tells us something totally mind-blowing. There is no such thing as an absolute empty void. The quantum vacuum is actually this bubbling, chaotic ground state of quantum fields, just brimming with zero-point energy. We can even measure the physical effects of this fluctuating nothingness right here in the lab, through phenomena like the Casimir effect. And this boundary, at the Big Bang, it forces us to question the nature of time itself. Intuitively, you and I experience what philosophers call presentism, the idea that only the now exists, the past is totally gone, and the future is unwritten. But the physics of relativity points us heavily toward eternalism, or the block universe theory. In this four-dimensional block view, the past, the present, and the future are all equally real. So our everyday experience of a flowing present might just be a trick of human consciousness and not a fundamental feature of the universe at all.
Now, check this out. This is the Wheeler-DeWitt equation. It's basically the quantum cosmological equivalent of the famous Schrödinger equation, meant to describe the quantum state of the entire universe. But if you look closely, there is absolutely no variable for time in there. None. In some quantum gravity frameworks, time simply doesn't exist fundamentally. Instead, it might just be an emergent illusion created by the entanglement of quantum particles. Think of it like temperature. A single atom doesn't have a temperature. It's just an emergent property of a bunch of moving atoms. Time might be exactly the same way.
Let's move to section 3, before the Big Bang, entering the realm of mathematical hypothesis. Because if time is just an illusion, does the word before even mean anything? Here's where we leave the established facts and enter the wildly fascinating realm of mathematical hypotheses. Cosmologists have come up with these incredible competing models to try and explain what classical physics just can't. The standard model gives us a singular Big Bang with no before. But look at these alternatives. Eternal inflation suggests our universe is just a bubble that stopped inflating in a past eternal inflating background. Loop quantum cosmology replaces the singularity with a quantum bounce, meaning the universe contracted before bouncing back into the expansion we see today. And Roger Penrose's conformal cyclic cosmology suggests this endless sequence of aeons, where the remote future of a previous universe becomes the literal Big Bang of our own. Obviously, none of these are proven yet, but they are absolutely brilliant attempts to explain the unexplainable.
All right, Section 4, Infinity and the Multiverse, pushing the limits of scale.
So if our universe is just one of many cycles, or maybe just a single bubble inside an eternal inflationary background, we inevitably crash headfirst into the concept of infinity. Cosmologist Max Tegmark actually categorized these speculative realities into 4 distinct levels. Level 1 is the most grounded. It's just regions of our own universe that are simply beyond our visible cosmic horizon. Level 2 represents those inflationary bubbles we just talked about, where entirely different laws of physics might apply. Level 3 comes straight from quantum mechanics, the famous many worlds interpretation, where every single quantum decision branches off into parallel realities. And then there's Level 4. This is the radical idea that every mathematically consistent structure physically exists out there somewhere.
Now, you might be wondering, why do physicists even entertain this stuff? Well, look at this number, 10 to the 120th power. This brilliant little calculation is the main culprit. When physicists try to calculate the vacuum energy of the universe using quantum field theory, the answer they get is 10 to the 120th times larger than the dark energy we actually observe causing the universe's expansion. To put that into perspective, it is the largest discrepancy in the history of physics. If the energy were actually as high as predicted, galaxies and stars could never have formed. So this staggering fine-tuning strongly suggests that our specific physics might just be a rare, perfectly tuned bubble floating in a vast, chaotic Level 2 multiverse. That brings us to Section 5, our limits of understanding and the biology of comprehension. Before we get completely lost in those infinite landscapes, let's just pause and ask a simple question. Why does thinking about this stuff literally hurt our brains? Well, the crucial point here is that we are biological creatures. We were optimized by evolution for hunting, gathering, and surviving on a middle-sized scale, not for calculating quantum cosmology. Cognitive neuroscience shows us that our numerical cognition is strictly logarithmic. We can easily intuitively grasp the difference between 3 and 4 apples, but without writing it down as symbolic math, we cannot intuitively picture the difference between a billion and a trillion. Plus, our brain acts as a predictive engine based on sensory input. Because things like the Planck length, a 4D block universe, or eternity have absolutely no sensory correlates, our brains just sort of short-circuit. We literally have a biological cognitive limit. But the limits aren't just biological. They might actually be mathematically woven into reality itself. Kurt Gödel's incompleteness theorems famously proved that any sufficiently complex mathematical system is going to contain true statements that simply cannot be proven within that same system. And on top of that, you have principles like computational irreducibility, which suggests that some physical processes can't be predicted with a neat mathematical shortcut. To know what happens, you literally have to simulate the entire system step by step. This implies there might be absolute, unbreakable rules preventing any mind from ever finding a simple shortcut to the complete laws of reality. Which brings us to the very edge of our epistemological journey. As we wrap up this explainer, I want to leave you with this final, provocative thought. We know that human cognition hits a biological wall when we try to intuitively grasp the quantum vacuum or the origin of time. But what about artificial intelligence? Will an advanced AI, operating with billions of parameters and completely unconstrained by biological evolution, one day easily grasp the physics of what happened before the Big Bang? Or, thanks to Gödel's theorems and computational irreducibility, are the ultimate truths of our cosmic origins permanently beyond the reach of any mind, artificial or biological? It's a question that challenges the very purpose of science, and honestly, it's one that we are only just beginning to explore.